Late August 1944, 06:15 hours. Observation Post 4, Pas-de-Calais, France. The morning report lay crumpled on a desk stained with coffee and cordite as German technical officers of Flak Regiment 155W stared at a single, impossible line of numbers. 82% destroyed. Through their rangefinders, they had seen it with their own eyes. V-1 flying bombs breaking apart in midair, dozens at a time, above the English Channel. Shells were bursting not in blind patterns, but precisely around the targets, as if guided by an invisible hand. To men trained in ballistics, it violated every law of probability they had ever been taught. Major General Max Wachtel, commander of the entire V-1 offensive, refused to believe his own data. In June, the British coastal gun belts had shot down barely 1 in 6 of his missiles. By late August, they were destroying 4 out of 5, and on this day, more than 8 of every 10. No tactical change, no training improvement, no known weapon could explain it. Something had altered the mathematics of the war overnight. Outside, V-1 launch crews loaded the stub-winged missiles with their 850-kilogram warheads, the Argus pulse-jet engines sputtering like mechanical hearts. Each weapon cost only 5,000 Reichsmarks to build and carried the promise of revenge for Germany's defeats in Normandy. London lay a mere 240 kilometers away, its factories and civilians within reach of a pilotless aircraft, too fast for most fighters to catch and too small for guns to hit directly, or so German engineers believed. Yet across the Channel, British observers watched the night sky fill with the fiery trails of V-1s and with the blinding bursts of anti-aircraft fire detonating so close to the incoming bombs that it seemed almost telepathic. Residents of Kent and Sussex counted the explosions and cheered when the engines fell silent midair. Some believed it was luck. Others suspected a new secret weapon. The truth lay inside the fuse of each shell, a device no larger than a matchbox, containing a miniature radio that could sense its distance to a target and detonate itself automatically. The Americans called it the VT Fuze, for variable time. The British called it the proximity fuse. Its existence was so secret that gunners were forbidden to recover duds. Naval patrols swept the Channel to sink any that fell unexploded. Only a handful of scientists and officers knew how it worked, and none imagined how decisively it would change the war. For the first time, anti-aircraft fire no longer relied on perfect mathematical prediction. The shells themselves could think, ending the era of blind shooting and turning near misses into certain kills. The results were mathematically impossible and utterly real. That morning, as Wachtel's staff rewrote their tables and checked their calculations again and again, the truth remained unchanged. 82% of Hitler's vengeance weapons had been destroyed in one day by an enemy technology the Reich did not know existed. How had this miracle of precision been conceived? And why had Germany's own scientists never seen it coming? The V-1 offensive was conceived as both a weapon and a message. After the failure in Normandy, Hitler demanded a blow that could reach across the Channel and remind Britain that the Reich still had teeth. The answer came from Peenemünde, where engineers under Major General Walter Dornberger and Werner von Braun had transformed years of experimental research into the world's first operational cruise missile. Each V-1 carried 850 kilograms of amytal, a mixture of TNT and ammonium nitrate, in its blunt steel nose. Propelled by an Argus AS 109-014 pulse-jet engine, it flew at roughly 640 kilometers per hour, too slow to be a true missile, yet too fast for the human eye to track in time for conventional gunfire. From the launch ramps hidden in the forests of northern France, the V-1s were fired toward London in an arc 240 kilometers long, guided only by a primitive gyroscopic autopilot. When fuel ran out, the engine stopped and the bomb dropped. Its droning pulse jet gave Londoners only seconds of warning before silence and impact. In the early weeks, the weapon seemed unstoppable. Fighter pilots chasing them down found the odds nearly hopeless. The RAF scrambled Spitfire, Twins, and Tempests, among the few aircraft fast enough to intercept. Pilots had to dive from altitude to gain speed, fire at close range, and then pull away before the bomb exploded. Even for skilled aces, success demanded perfect timing and luck. Anti-aircraft gunners using conventional timed fuses had even less chance. The shells had to be set by hand for each burst altitude, calculated against speed, range, and trajectory, often in poor light or foul weather. By late June 1944, the results were grim. For every V-1 destroyed by gunfire, thousands of shells were expended. Only about 17% were shot down before reaching England. The rest landed among homes, hospitals, and railway stations. The British War Cabinet feared that if the bombardment continued at this pace, civilian morale could collapse. In 10 days, 1,600 people were killed and nearly 4,000 injured. The campaign became known as the Robot Blitz, a phrase that carried both awe and terror. The British response evolved rapidly. Within days of the first attacks, the Air Ministry ordered a complete reorganization of southern England's air defense network. Radar stations along the coast began to track the incoming missiles. The Royal Observer Corps plotted their courses and relayed warnings to anti-aircraft command. Fighter squadrons were repositioned from Europe to home defense. The RAF even experimented with intercepting V-1s by tipping their wings, a dangerous maneuver in which pilots nudged the missile's wing with their own to destabilize its gyro and send it crashing short of target. It was daring, but unsustainable. The problem lay in physics, not courage. A V-1 presented a cross-section smaller than a fighter aircraft, moving at twice the speed of most bombers. Predicting the exact moment a timed fuse shell would intersect that path required split-second accuracy. Even with radar assistance, the calculation had to be fed manually to each gun crew. Any error of more than half a second meant a miss by tens of meters. The gunners were shooting blind, filling the air with steel in hopes of coincidence. But by July, something remarkable began to happen. Reports from the gun belts around Dover and Folkestone showed sudden improvements. Whole waves of V-1s were exploding before they reached land, hit by shells that seemed to know precisely where to burst. German observers along the French coast noticed that British fire patterns had changed. Bursts appeared closer to their targets, more centered and more lethal. The gunners, it seemed, had acquired a precision that defied experience. Unbeknownst to the Germans, the change came from across the Atlantic. 2 years earlier, in the laboratories of the United States Navy and the Office of Scientific Research and Development, physicist Merle Tuve and his team at the Johns Hopkins Applied Physics Laboratory had achieved what most scientists believed impossible. They had created a fuse that could sense its distance from a target. Using miniature radio transmitters, it emitted continuous waves that bounced off nearby objects. When the returning signal reached a specific strength, a circuit triggered the shell's detonation. No wires, no timing key, no human adjustment, just a self-contained electronic brain that could make a decision faster than any gunner. The first prototypes were tested secretly in 1942. They worked only intermittently, often destroyed by the violent shock of being fired from a gun. Standard vacuum tubes shattered under 20,000 times the force of gravity. Batteries failed to activate after months of storage. The fuse had to survive heat, pressure, and spin, 25,000 revolutions per minute, and still respond within milliseconds when approaching a target. By late 1943, American engineers had solved the problems through brute industrial persistence. Miniature tubes, originally designed for hearing aids, were reinforced and mass-produced. New batteries were created to activate instantly upon firing. Each fuse contained a radio transmitter, receiver, and amplifier, all sealed inside a casing smaller than a coffee cup. The result was a miracle of precision engineering. When attached to an anti-aircraft shell, the proximity fuse transformed it from a blind projectile into a hunter. It did not need to hit the target directly. It only needed to come close enough for its radar pulse to sense metal and detonate. What had once required 1,000 shells could now be achieved with 100. Britain's scientists had known of the concept, but lacked the capacity to mass-produce such delicate electronics. The United States did. By 1944, American factories were producing tens of thousands of fuses every day under conditions of absolute secrecy. The devices were shipped across the Atlantic, disguised as VT variable time equipment, a deliberate misnomer meant to deceive any spies. When the first batches arrived in Britain, General Sir Frederick Pyle, commander of Anti-Aircraft Command, personally oversaw their distribution. He had one order. No shell containing the new fuse was to fall intact into German hands. To guarantee that, he redeployed gun batteries to the southern coast so that any unexploded rounds would land in the channel. Gunners received sealed crates marked with serial numbers and strict instructions. They were never told why these particular shells worked better. They simply fired and watched the results speak for themselves. By the end of July, the statistics were astonishing. The interception rate of the southern gun belt rose from 17% in June to 55% in July. Pilots returning from patrols reported seeing strings of V-1s explode in midair without a single fighter's gunfire. The sky over Kent had become a lethal curtain. London, battered and burned for weeks, began to breathe again. Across the channel, German engineers studied the data in disbelief. They had calculated that the chance of a 3.7-inch anti-aircraft shell hitting a V-1 was less than 1 in 10,000. Now, hundreds were falling daily. The mathematics had changed, and none of their experts could explain how. By late August 1944, the impossible became routine. British guns were destroying over 3/4 of the incoming missiles, and on one day, 82%. The flak gunners, who once fired blindly, were now executing the most successful air defense operation in history. In Berlin, the news caused panic among the scientists at Peenemünde. Reports from occupied France mentioned shells that exploded in the vicinity of the V-1s rather than on contact. German physicist Ernst Steinhoff dismissed it as exaggeration. "A shell cannot think," he told a colleague. "It cannot decide when to explode." But something had indeed begun to think. Tiny circuits, sealed in steel and glass, mass-produced by the millions in American factories. They were invisible to German intelligence, invulnerable to sabotage, and impossible to replicate in time. How had such a secret been kept so perfectly? And how did a few grams of circuitry come to wield more power than all of Germany's vaunted wonder weapons combined? The secret that turned statistics into certainty was hidden inside a cylinder no larger than a man's thumb. Engineers called it the variable time, or VT Fuze, a term chosen to conceal its true nature. In reality, it was the world's first practical proximity detector, a self-contained radar that transformed a simple shell into a guided instrument of a precision. Inside its small aluminum case, the VT Fuze carried an entire radio system compressed into the most hostile environment imaginable. A transmitter emitted a continuous radio wave through an antenna embedded in the shell's nose. When the wave struck a nearby object, an aircraft wing, a missile fuselage, or a flying bomb's engine, it reflected back toward the fuse. The receiver detected the returning signal, measured the change in amplitude, and when the reflected energy grew strong enough to indicate closeness, a circuit-triggered detonation. The principle was simple. The execution required the impossible. Every fuse had to survive being fired from a gun barrel, enduring more than 20,000 times the force of gravity in acceleration and spinning at over 25,000 revolutions per minute. The impact shock could crush steel, yet the fuse's fragile glass vacuum tubes had to remain intact and functional. The temperature climbed to 250 degrees Celsius within a second, and the electronic components had to operate perfectly after that violence. The solution came from America's industrial laboratories. In 1941, Dr. Merle Tuve at the Johns Hopkins Applied Physics Laboratory began designing a miniaturized, ruggedized radio fuse. He worked with Sylvania Electric, Western Electric, and General Electric to produce tubes small enough to fit inside a 40-millimeter shell, but strong enough to endure the firing shock. These acorn tubes use thicker glass and internal supports to resist vibration. New dry cell batteries, sealed in metal and activated by acceleration upon firing, provided power for exactly 40 seconds, the shell's flight time. Each component demanded unprecedented precision. A single misalignment of a millimeter would destroy the circuit. American factories developed mass production lines where women with magnifying glasses soldered circuits under microscopes, assembling parts smaller than the head of a match. Quality control was obsessive. Every fuse was tested in vibration rigs, drop towers, and live firing ranges. Out of thousands produced, fewer than 2% failed inspection, a miracle for wartime manufacturing. When fired, the fuse did not think in human terms, but it behaved as if it did. The radio signal oscillated between the transmitted and reflected waves, creating a beat frequency that grew stronger as the shell neared its target. The circuit detected this interference pattern, and within milliseconds, triggered detonation. The result was a perfect burst, close enough to shred wings or detonate a warhead, but not so near that the fragments missed entirely. Compared to traditional time fuses, which relied on mechanical gears or manual setting, the VT fuse was self-adjusting, self-arming, and self-destroying. It could function in rain, darkness, or cloud, unaffected by altitude or visibility. It made every anti-aircraft gunner, no matter how inexperienced, into a mathematical prodigy. By early 1944, the United States was producing 40,000 fuses per day. At its peak, 110 factories employing over 80,000 workers were dedicated to the program. Crosley Corporation, which once made radios and refrigerators, converted its entire operation to fuse production, 16,000 units per day from a single plant. The cost dropped from $732 per fuse in 1942 to less than $20 by 1945. In total, America built more than 22 million of them. Germany, with its fragmented research institutions and reliance on handcrafting, could never have achieved such scale. Its scientists had studied similar principles since the 1930s, but abandoned them as impractical. They concluded that no vacuum tube could survive artillery acceleration. They were right, until the Americans proved otherwise. What made the VT Fuze revolutionary was not only its design, but its philosophy. It represented a shift from complex, one-of-a-kind weapons to simple devices multiplied by industry. Every improvement in production made every gun more lethal. Instead of building one perfect weapon, the Allies had built millions of perfect components. In combat, the difference was immediate. Against aircraft, the VT Fuze increased effectiveness by 5 to 10 times. A destroyer's anti-aircraft battery could now repel air attacks that once guaranteed destruction. In the Pacific, Japanese dive bombers were shattered mid-dive before they could release torpedoes. By the time the fuses reached Europe, they had already changed the balance at sea. Now they were about to change it over London. As British gunners loaded shells with the new device, They noticed only a difference in color coding and handling procedures. They were told nothing of what lay inside. The secrecy was absolute. If a single fuse fell into enemy hands, the Germans might replicate it, or worse, develop countermeasures. To prevent that, every dude fired toward the channel had to be destroyed or recovered at once. The gunners didn't need explanations. They saw the results. Shells that once filled the sky with random bursts were now detonating directly beside the V-1s, tearing them apart with precise rings of shrapnel. The air above the channel had become a field of invisible geometry, ruled by unseen radio waves. The mathematics of chance had turned into certainty, and for the first time in the air war over Britain, technology, not courage, was deciding who lived and who died. If this technology was so extraordinary, who had the vision and the secrecy to bring it from the laboratory to the battlefield in time to stop Hitler's vengeance weapons? The path from concept to battlefield victory began in laboratories that barely existed before the war. In 1940, as German bombers darkened British skies, a small group of American scientists met at the Carnegie Institution in Washington, D.C. Among them was Dr. Merle Tuve, a physicist from Johns Hopkins University, whose research had focused on cosmic rays. His proposal was audacious: to create a fuse that would make shells explode automatically when close to a target. At the time, even sympathetic colleagues called it a dream for the next century. Tuve disagreed. He argued that the principle already existed in civilian radio: transmission and reflection. All we must do, he told his assistant, reconstructed, is make the shell know when it is near something. The problem was how to compress a radar system into a projectile that would survive the violence of being fired. No one had ever succeeded. The U.S. Navy sponsored the experiment through the newly formed Office of Scientific Research and Development. It was assigned to the Applied Physics Laboratory, a division created overnight for this purpose. At first, the project was little more than a workshop filled with oscilloscopes and discarded radio parts. Within months, it became one of the most advanced electronic laboratories in the world. Engineers from Western Electric, RCA Sylvania, and General Electric were summoned to collaborate. Their progress came in increments measured by failure. Early tests saw fuses detonate in the gun barrel, shattering weapons and scattering fragments across proving grounds. Others failed to detonate at all. Tuve's team learned to think like engineers and soldiers at once. They tested each component for shock tolerance, spun tubes in centrifuges, and fired dummy shells into sandpits. The work demanded secrecy and endurance. Every breakthrough carried the same instruction: tell no one. In 1941, Britain's scientific mission to the United States, known as the Tizard Mission, shared radar and jet technology in exchange for American support. Among the documents were notes describing early British attempts at proximity fuses. The British scientists had achieved laboratory success, but could not build them in quantity. American industrial capacity provided the missing element. From this alliance, the modern fuse was born. By 1942, the first operational prototypes reached naval test ranges in Virginia. When a destroyer fired one at a towed target aircraft, observers watched in disbelief as the shell exploded precisely near its mark. The radio waves had done their work. The Navy classified the test results immediately. The entire program was placed under code word VT, a deliberate misdirection implying variable time, not proximity. The true principle was revealed only to a handful of officers. Production began under extreme compartmentalization. Each factory built a different component: tubes in one, batteries in another, timers in a third. No single worker knew what the final device did. As Tuve later explained, secrecy was our armor. The penalty for carelessness was dismissal or prosecution under wartime secrecy laws. The result was silence, an industrial conspiracy sustained by patriotism. Meanwhile, Allied intelligence services monitored German research. The British Secret Intelligence Service had captured fragments of German correspondence describing radio fuse, but found no operational models. Luftwaffe engineers had tried to develop similar devices since 1938, but their components shattered under acceleration. German physicist Ernst Meissner declared the concept impractical within 10 years. That conclusion blinded the Reich to its enemy's progress. By mid-1943, the VT Fuze was already changing the Pacific War. U.S. Navy gunners used it to defend against Japanese dive bombers, achieving kill rates 5 times higher than before. Reports reached London through secure channels, but even within Allied command, the weapon's existence was treated as rumor. Churchill himself was briefed only in broad terms. A new American fuse with remarkable self-detonating qualities. He approved its limited use against Germany, but warned that if a single unexploded example were recovered, the advantage would vanish overnight. The coordination between Allied laboratories became an invisible front line. Scientists in Britain modified the American design to fit British shells and radar-controlled guns. At Fort Halstead and Woolwich Arsenal, small teams worked under armed guard, adapting fuses for anti-aircraft artillery. Test ranges on the southern coast were cleared for secret firings. Only the officers directly involved knew what the new shells contained. Even within the U.S. military, access was restricted. Artillery officers received crates marked VT, handle with care. Instructions specified firing angles and distances, but said nothing about the technology inside. Some gunners thought it was a timing mechanism. Others joked that it contained magic powder. None imagined that each shell carried a functioning radar. By the spring of 1944, as Allied troops prepared for D-Day, production reached levels sufficient for continental defense. Thousands of fuses were shipped to Britain under armed escort. They traveled in unmarked convoys, guarded as tightly as atomic materials. Only a few senior officers, men like General Frederick Pyle and Admiral Blandy, understood the stakes. One engineer later recalled, "We were told our work might save a city or win a war, but we would never be able to say how." Reconstructed. The scientists never saw their invention in action. Their laboratory data became reality only when the first V-1s streaked toward London. The gunners who loaded the shells didn't know they were wielding one of the most advanced pieces of electronics ever created. The Germans who watched their weapons disintegrate in midair didn't know they were witnessing the triumph of physics over arrogance. But in August 1944, that silence, the silence of secrecy and of the laboratories that birthed it, was about to echo louder than any explosion. How would the Allies deploy this invisible technology into the chaos of real combat? And could it maintain its secrecy under fire? By July 1944, the weapon was ready, but its success would depend on how quietly it could be used. The proximity fuse had reached Britain in plain crates labeled VT Fuses, variable time. The deliberate misdirection printed even on shipping manifests. Each batch arrived under military escort, moved at night, and stored in guarded depots near the southern coast. No gunner was told its true purpose. Only a handful of officers at Anti-Aircraft Command and the Ministry of Supply knew that each shell contained a miniature radar. General Sir Frederick Pyle, the man responsible for defending London from aerial attack, faced a dilemma. If a single fuse failed to detonate and landed intact on French soil, the Germans might recover it. That would end the secret in a day. Pyle ordered the gun belts to be redeployed southward, close enough to the channel that any dud shell would fall into the sea. Gunners protested. The move reduced their firing angles and shortened their engagement time. Pyle insisted. The technology was too valuable to risk. To use the new fuses effectively, the entire air defense system of southern England was rebuilt. Radar stations were upgraded with American SCR 584 fire control systems, compact radar units capable of locking automatically onto a target and feeding its range and speed directly into mechanical predictors. These computers, in turn, aimed the guns. The gunners no longer estimated by eye, their weapons followed radar instructions, transmitted by electric cables. Human intuition was replaced by calculation. The new coordination required discipline. Each gun position consisted of 4 3.7-inch heavy anti-aircraft guns arranged in a square, linked to the radar truck by telephone cable. Nearby, plotting crews monitored screens as blips appeared over the channel. When a V-1 crossed the coast, the radar automatically tracked it. The predictor computed its course, and the gun layer waited for the firing order. Once the shells left the barrel, the fuses did the rest. The results came almost immediately. In the first week of August, the Southern Gunbelt's success rate climbed to over 60%. Gunners described the difference in simple terms. Before, we fired at where we hoped they'd be. Now, the shells seemed to find them. Reconstructed. Firing drills changed accordingly. Instead of random barrages, batteries now fired controlled patterns called curtains. Each curtain was a calculated wall of explosions, timed to detonate as the V-1s crossed fixed zones. The VT Fuze amplified the effect, creating an invisible net of lethal fragments. German observers later reported that V-1s entering the zone often disintegrated without visible hits. To the watchers, it looked like sorcery. The guns themselves became part of an integrated system. Radar, predictors, and communications linked dozens of batteries into a single organism, directed from London's operations room at Stanmore. There, under flickering lights and cigarette smoke, officers tracked every incoming missile. The telephone lines hummed with coded reports. Plot, C-27. Crossing Dover, altitude 600 meters, speed 640 kilometers per hour. Within seconds, the nearest battery received firing coordinates. A typical engagement lasted no more than 30 seconds. A V-1 was detected at 25 kilometers. At 15, the guns opened fire. At 10, radar tracking adjusted continuously as the missile's engine note droned overhead. At 5 kilometers, the first shell detonated nearby, and the drone ended abruptly in silence. A cheer usually followed. Then another blip appeared on the screen, and the cycle began again. Even with its success, secrecy was relentless. Every fired shell had to be accounted for. Crews were forbidden to retrieve fragments or discuss performance. Naval patrols scoured the channel to sink unexploded shells. Fighter command pilots flying above the gun belts were instructed to stay clear. No one wanted a Spitfire destroyed by a fuse meant for a flying bomb. By the third week of August, the integration of radar, guns, and proximity fuse had created the most advanced air defense system the world had ever seen. Each improvement multiplied the next. Radar precision enhanced fuse effectiveness, and fuse reliability gave radar its purpose. The V-1 offensive, once a terror without counter, was now a predictable equation with a fixed result. But the weapons kept coming. From hidden ramps in the Pas-de-Calais, German crews launched hundreds each night. The pulse jets flickered like fireflies across the channel. Londoners heard them and counted the seconds between engine cutout and explosion. The silence that followed often meant survival. The British gunners, exhausted but confident, fought their invisible duel in shifts that blurred day and night. Each firing produced its own rhythm, the deep concussion of guns, the echo rolling across coastal fields, and then, in the distance, the muffled crump of another intercepted bomb. They did not see the fuse's radio pulses or understand their inner workings. They only knew that for every shell fired, the odds of survival improved. At dawn, the fields along the Kent coast were littered with fragments, twisted steel from V-1s that had failed to reach their targets. Farmers grew accustomed to the wreckage, marking each impact with a small flag for disposal teams. For the first time since 1940, Londoners awoke to headlines that spoke of progress, not despair. And then, near the end of August, something extraordinary happened. The calculations, already impressive, reached their mathematical peak. Out of every 100 V-1s launched, 82 were destroyed before they crossed the English coast. The figure astonished even the men who fired the guns. It marked not just a victory of defense, but a demonstration of what coordinated science and industry could achieve under pressure. The question within Allied headquarters was no longer whether the proximity fuse worked. It was how long they could keep it secret. If the Germans ever discovered what truly powered those shells, could they adapt? Or had the technological race already ended without them knowing? August 28, 1944. Dawn spread over the English Channel like cold metal. The night's mist still clung to the hills of Kent, muffling the distant thunder of the guns. At 0543, radar station C-17 at Swingate picked up the first cluster of contacts. Small echoes moving at 640 kilometers per hour, steady altitude, heading northwest. The V-1s were coming. In the operations room at Stanmore, officers leaned over the plotting table as wax markers traced the missiles' paths. The rhythm was familiar, too familiar. Reports had streamed in for weeks, but something about this morning was different. Atmospheric conditions were perfect. The wind over the channel was calm, the radar beams steady, the gun crews rested after a rare clear night. General Pyle had ordered maximum readiness. Every battery manned, every shell accounted for, every radar synchronized. At 06 Awooks, the first guns opened fire. From Dover to Dungeness, the coast erupted in disciplined thunder. Each battery worked like a machine, radar locked, predictors fed data, and shells streaked skyward in precise salvos. The bursts appeared as golden sparks above the pale water. Through binoculars, observers saw the first V-1 shatter midair, its fuel tank igniting into a falling streak of fire. Seconds later, another followed, then another. In the control truck of the 146th Heavy Anti-Aircraft Regiment near Folkestone, Lieutenant Arthur Robson recorded his impressions in a field log. "The air was alive," he wrote later. "We could see them burning in every direction. It felt as if the guns had learned to think." Reconstructed quote, "For the men at the guns, the difference was physical. Before, they had fired blindly into gray skies. Now, every detonation seemed preordained, timed to perfection. The shells burst close enough to tear apart the missiles without visible contact. The air filled with the sharp metallic hiss of fragments slicing through space. Radar crews watched their scopes bloom with fading echoes as each V-1 vanished. By 0630, the network was fully engaged. 38 incoming missiles were tracked simultaneously. The SCR-584 radars hummed and rotated, feeding continuous data to gun layers who rarely looked up from their instruments. They trusted the circuits now. When the firing orders came, the sequence was mechanical. Aim, fire, reload, fire again. The tempo of industrial war reduced to seconds. Over the channel, the V-1s fell one after another, detonating mid-flight or plunging into the sea. Only a handful managed to cross the coast, most too damaged to continue. One exploded harmlessly over the marshes near Rye, another disintegrated near Ashford, its engine debris scattering across a farm field. At 0715, observers at Capelle-le-Fern reported that the horizon glowed with dozens of falling fires, each a flying bomb destroyed before reaching its target. At Stanmore, General Pyle received the morning's interim figures. 212 launches detected, 174 confirmed destroyed before reaching land. That represented more than 80%. He read the report twice before initialing it. "We may be witnessing the end of the V-1," he said quietly to his staff. Meanwhile, across the Channel in northern France, German radar operators at Marquise and Ouessant watched their tracking screens with growing confusion. Dozens of launches showed premature signal loss, no return echoes beyond mid-channel. They assumed malfunction, perhaps fuel failure. Officers telephoned Peenemünde to report abnormally high losses in transit. At first, analysts blamed sabotage or mechanical wear. None considered that the missiles were being destroyed in the air by a weapon they did not believe possible. Back in England, anti-aircraft gunners worked until their shoulders ached and their ears rang. The smell of cordite coated the dawn air. Between bursts, they wiped sweat from their faces and waited for the next radar call. For many, it was the first time in years that victory felt tangible. Not a distant rumor, but a reality they could see with their own eyes. By noon, the sky had cleared completely. Smoke from burned V-1s drifted over the Channel in long gray ribbons. The day's statistics were compiled by evening. Of 272 flying bombs launched, 224 destroyed, 33 damaged or crashed short, 15 reached London. The final interception rate, 82.3%, the highest ever recorded. That night, newspapers printed cautious headlines. "Flying bombs checked. Defenses improve again." The details remained secret, but morale surged across Britain. In pubs and shelters, Londoners whispered that the gunners had found a way to sense the bombs. They were right, though none of them could have known how literal that word was. At Peenemünde, the reports caused disbelief and anger. Technical officers compared launch logs, weather data, and manufacturing records. Nothing explained the losses. Wachtel, commander of Flak Regiment 155W, telephoned Berlin to report an inexplicable rise in enemy interception efficiency. When asked for a cause, he replied simply, "We have no explanation consistent with known science." The truth was buried under layers of secrecy on both sides. The British gunners credited radar, the Germans blamed luck, and only a few scientists in America and Britain understood that the real battle had been fought by circuits invisible to the human eye. As night returned over the Channel, the searchlights dimmed, the guns fell silent, and the crews cleaned their barrels. The day's work was done. 82% of Hitler's vengeance weapons had never reached England. The defenders didn't celebrate. They were too exhausted to grasp what they had achieved. But in that exhaustion lay the quiet turning point of a war fought not just with courage, but with invention. What did the Germans believe had happened that day, when their flawless machines began falling from the sky without reason or mercy? In France, the officers of Flak Regiment 155W studied their charts until the lines blurred. The mathematics would not reconcile. Engine reliability had improved, air routes had been adjusted, launch timings optimized, yet losses increased. From Peenemünde to Paris, reports flowed upward, filled with contradictions. The missiles were not exploding prematurely, nor falling from mechanical failure. They were simply vanishing. At first, the Reich's technical command blamed poor workmanship. V-1s were being built in underground factories by slave laborers, men and women from concentration camps, starving, beaten, desperate. Sabotage seemed plausible. Dozens were executed on suspicion, but the results did not change. Each night, hundreds of new flying bombs disappeared over the Channel, leaving only ripples on radar. Intelligence officers attempted pattern analysis. They noted that losses were highest when visibility was clear and winds calm. One report suggested that British radar might have improved, directing fighters or guns more accurately. Another argued that the British had developed a new kind of aerial minefield, a cloud of small explosive balloons detonated by radio control. The theories multiplied, none supported by evidence. In August, General Max Wachtel demanded a full technical audit. Over several nights, German technicians launched test missiles fitted with cameras and barometers to record trajectories. The films showed nothing unusual: no enemy aircraft, no balloon cables, no intercepting weapons. The bombs simply ceased transmitting after crossing the coast. Wachtel's staff began suspecting jamming, perhaps a British device disrupting the missile's gyroscope. But the V-1 guidance used only mechanical controls. There was nothing to jam. At Peenemünde, senior engineers argued fiercely. Some insisted the Allies had discovered a method to predict launch times through espionage. Others claimed that British gunners were firing pre-detonating shells, though physics said such accuracy was impossible. Dr. Robert Lusser, who had designed the V-1's control system, dismissed the idea entirely. "No gun can think," he said. "They are guessing, and guessing well." Still, the data could not be denied. The ratio of launches to arrivals at London continued to collapse. The once proud engineers who had promised Hitler a weapon of terror now faced humiliation. "Either the English are lucky," one officer wrote bitterly, "or they have gods on their side." Even German intelligence failed to notice the clues in front of them. The Oslo Report of 1939, an anonymous document sent to British intelligence at the war's start, had mentioned Allied work on radio-controlled fuses. German scientists at the time had dismissed it as Allied propaganda. Years later, that neglect became fatal. Captured V-1 fragments told them nothing. The British had carefully moved their gun belts to the coast so that no unexploded fuse could land on French soil. Luftwaffe reconnaissance showed nothing unusual except for a new density of radar stations and gun sites. The Germans concluded the British were simply using more weapons. By the time the truth surfaced, long after Germany's defeat, the shock was profound. The proximity fuse violated everything the Reich's physicists had believed about electronics, miniaturization, and manufacturing. They had assumed such devices impossible, and that belief had become a weapon against them. In late 1944, a German officer captured in the Ardennes was shown a recovered Allied proximity fuse. He turned it over in disbelief, then said softly, "If we had this, we might have won the war." Reconstructed, but they had not. Their science had stalled under secrecy and ideology. Their factories had traded precision for cruelty. Their engineers, once the envy of the world, had been overtaken by men who built radios and hearing aids and turned them into the most precise, killing instruments in history. How would the outcome of the war shift once the Germans realized that Britain's salvation had come not from the sky, but from the laboratories and assembly lines of a democracy they had dismissed as weak? By September 1944, the V-1 campaign was collapsing under its own arithmetic. Between June and August, Germany had launched 9,121 flying bombs toward England. Only 2,515 reached London. Nearly 7,000 had been destroyed by anti-aircraft guns, fighters, or mechanical failure. The proximity fuse had turned a weapon of terror into an equation of diminishing returns. The cost to Germany was immense. Each V-1 consumed scarce fuel, steel, and slave labor from underground factories like Mittelwerk. Every launch that ended in the Channel represented wasted effort and human suffering. Hitler had promised a vengeance weapon that would crush British morale. Instead, it became a symbol of futility. Londoners still died, 6,184 killed, nearly 18,000 wounded, but the capital never broke. General Frederick Pile's command had achieved what even the RAF during the Blitz had failed to do: render the enemy's strategic bombing ineffective. His analysts calculated that without the proximity fuse, casualties might have been 4 or 5 times higher. The weapon had not only saved a city, but preserved the morale of an entire nation. In Berlin, the failure of the V-1 forced desperate improvisations. The Luftwaffe shifted to night launches, hoping darkness would mask the missiles from radar. It did not help. The British had refined their detection systems and recalibrated their gun belts. Even unseen, the V-1s could not outrun radio waves. When the losses continued, the Germans switched to the V-2 rocket. Faster, higher, unstoppable. But it was a strategic dead end. Each V-2 cost the labor of thousands, yet carried only a single ton of explosive. The campaign consumed resources that might have built hundreds of fighter aircraft. For the Allies, the success of the proximity fuse carried consequences far beyond Britain. Its performance convinced commanders that electronics, not armor or speed, would define the next stage of warfare. In the Pacific, U.S. Navy fleets used the same fuse to shatter kamikaze attacks, saving countless ships and crews. In Europe, however, the weapon remained secret. Even Allied field artillery was forbidden to use it on land for fear an unexploded shell might reveal its design. Thousands of soldiers died in conventional bombardments that might have been prevented. Only during the Ardennes offensive, when German forces broke through the American lines, did the War Department finally authorize its use in Europe. The results were immediate. Entire infantry formations shattered by artillery that seemed omniscient. When the war ended, the proximity fuse was declassified. Its numbers spoke for themselves. 22 million produced, used in every theater, credited with saving tens of thousands of lives. American and British scientists revealed that the total cost of development, about $1 billion wartime dollars, had yielded a return measured not in profit, but survival. For Germany, the revelation was humiliating. Their wonder weapon, built in secrecy and suffering, had been defeated by a small glass bulb containing circuits and a battery. The proximity fuse embodied everything the Reich had dismissed as trivial: mass production, industrial collaboration, scientific openness. It was the antithesis of their ideology. The V-1 campaign's failure marked more than a technological defeat. It symbolized the turning point of industrial warfare itself, a war no longer decided by valor or genius alone, but by systems, machines feeding machines, guided by invisible signals. If a tiny device could save London, what other miracles of engineering were waiting in laboratories across the Allied world, shaping wars yet to come? When the war ended, the secret was finally revealed. On September 9, 1945, the U.S. War Department issued a statement calling the proximity fuse one of the 3 most important weapons of the war, surpassed in effect only by radar and the atomic bomb. For the German scientists who read those words, the revelation was a second defeat. They had spent years believing the Allies had simply outnumbered them. Now they understood. They had been outthought, outproduced, and out-coordinated. The device that defeated the V-1 was not born from a single genius, but from cooperation on a scale totalitarianism could not match. Thousands of engineers, machinists, and factory workers, most of them ordinary civilians, had contributed without ever knowing what they were making. In plants, from New Jersey to Ohio, women soldered filaments thinner than hair under magnifying lenses, working 12-hour shifts. Each fuse they built carried within it the precision of a national will harnessed to science. The lesson extended far beyond the battlefield. In Germany, knowledge had served power. In America and Britain, power had served knowledge. The proximity fuse proved that open exchange among scientists between laboratories across industries could create weapons no single secret institution could rival. It turned radio engineering into a shield, not just a sword. After the war, many of its inventors returned to universities. Their wartime experience birthed new fields: guided missiles, radar altimeters, electronic navigation. The VT Fuze became the ancestor of modern air defense systems and the silent foundation of the Cold War's deterrent balance. What had once been a weapon to save London evolved into the principle that defined future warfare: automation, precision, and speed. For Londoners who had lived through the summer of 1944, its impact was more human than technical. They remembered the nights when the sky roared with engines and fell silent with fear, the mornings when the newspapers counted the bombs that hadn't landed. Few ever knew why the explosions in the distance had grown fewer, or why the city had survived. Their salvation had come from scientists they would never meet, through devices smaller than a clenched fist. In the ruins of Peenemünde, captured German engineers examined the American fuse under Allied supervision. Many simply stared at it in disbelief. They had built rockets that reached the stratosphere, but had failed to build a transistor that could think. "We were artisans," one of them admitted years later. "They were manufacturers." Reconstructed quote. The contrast summarized the war's final truth. The age of craftsmanship in destruction was over. The future belonged to systems, to production lines, to the invisible logic of science serving democracy. The proximity fuse's quiet pulses had done more than destroy flying bombs. They had signaled the beginning of a new world, a world where wars would be fought by electrons, where factories would decide what generals could not, and where nations that mastered mass coordination would always defeat those that worshipped isolated genius. In late August 1944, as shattered V-1s burned out over the Channel, no one on either side could see that future clearly. But it had already begun, written in radio waves, soldered in glass, and proven by mathematics in the skies above London. And perhaps that is how every great change in war begins, not with the loudest explosion, but with the smallest spark of intelligence that no enemy can see coming.